So good morning everyone. In this talk I will explain about our paper Tactile-ViewGCN, learning shape descriptor from tactile data using Graph Convolutional Network. So in this presentation I will go through the problem statement and the dataset we used for our problem and few related works and how they usually solve this problem and the intuition behind our method, and in detail we'll go through the method section also where we see like what model we used and what architectural components it consists of, and we'll go through the experiment sessions and also finally the conclusion and future works. So the main problem statement is like for humans, like our sense of touch really helps us with our day-to-day activities. So there was a previous experiment conducted where they injected anesthesia into volunteers' hand and they were asked to perform activities like picking up an object, moving it and just manipulating these objects, and they found it like the volunteers found it really difficult to do these activities after getting this anesthesia. So this tells us that like for humans, like along with the visual data, we heavily rely on tactile information to perform this object manipulation. So this could be true for robots also, and giving robots this capabilities to get this tactile feedback could really help in doing performing activities like object manipulation. So how does robots get this tactile feedback? So for enabling robots to get this tactile data, usually tactile sensor is used. So these sensor basically measure the pressure at the contact area in these sensors. So our main problem statement is to enable robots to identify object from just this tactile data, so which is basically the pressure imprint left by that object. So these could be really helpful in cases where when you can't fully rely on this camera sensor. In those cases, like this could be a really good application. So let's go through the dataset. So in our problem we use MIT STAG dataset. So in this dataset, like tactile sensor array is knitted on a glove, and then finally this is how it looks like, and this glove is used to grasp multiple objects in the dataset. Specifically there are 26 objects in this dataset, and when we grasp and do this manipulation, all these sensors measure the pressure at each point of contact, and these tactile data is finally used for classification. And this is how it looks like. Wherever there is contact, like there will be high values, and if there is no contact, like it will give a low pressure value. So this is how the dataset creation pipeline looks like. So a person will hold different objects in different areas, and continuously these data are streamed and saved as a tactile frame as shown as here. So we can, since there are 124 sensor arrays, we can resize it into a 32 cross 32 image, and this is how the image will look like. It's a single channel image where the pixel values represents the pressure at that point of contact. So in total this MIT STAG dataset consists of 135k frames of tactile images, and each frame is a single channel image with 32 cross 32 dimension, and there are in total 26 different object classes in that dataset that we want to classify. And but for training we curate this dataset and finally get 36k frames for training, because like in this dataset, like there are many frames where the glove is used to not grasp any object, like it's empty, and so those empty frames has no useful information. So after removing this, like we have around 36k frames for training and 16k frames for testing. And also like for testing, usually most methods they don't use single frames, because like it's very difficult to classify an object just from single frame of tactile data. So usually they take around 15 to 20 frames as an input and use those 15 to 20 frames of the tactile data corresponding to that object and use that for testing. So that's what we do in our problem also. So let's go through some of the related work. So many methods, what they usually do is they use CNN to extract features, and then they just concatenate it and use an MLP layer to do classification. So they use a ResNet 18 model to get this feature from all these tactile images, and then they just concatenate it and then use an MLP to do this classification. So here they don't actually consider any explicit relationship between these different tactile images. They just let the model learn everything. Another popular way of solving this problem is considering this as a sequential problem. So basically we have around n frames of input, and we want to predict a single scalar value of the output class. So this is similar to the sequential problem of many to one problem. So here you can then just take this tactile images, pass it through a scene, and get this image features, and then you'll have n number of features, and you just want to predict a single output value, and for that you can use sequential models like RNN or LSTM and do this. So this is another popular method, but here also like the model has to learn everything in between, like the relationship between these features that are covering different parts of the object. So there is no explicit geometric information. So our main intuition and idea is based on this. So let's assume like we blindfold your eye and tell you to hold out your hand, and like another person constantly place an object at different angle and ask you to identify this object. So let's assume in our case, like we are placing a cube. So when you place this cube on your hand, like you'll just feel a flat surface, and another person will constantly rotate this and place different cube face on your hand, and when we ask what is the object, like we will find it very difficult because we just feel a flat surface and we don't know like whether they rotated it or just kept the same face, or some of the face are flat, and so it's very difficult to classify an object from just this tactile data. So but like if the another person gives information like so this is the first angle, like after this first angle, like I rotate it by 90 degree, so and after that he places the object again. So if he does that, like now you know like from all the 6 views, like it's a flat surface, so it's either a cube or cuboid. So in both these cases, like we'll have the same tactile pressure data, but just by adding this view angle information for this corresponding tactile frame, we can do this classification and it becomes an easier task. And this is similar to 3D shape classification from multi-view images, which is a well explored topic. So our main idea is based on that. So to solve this, we have 3 major challenges. So how to get this viewing direction from this unlabeled tactile images, and after getting this viewing angle, how to aggregate these features such that like this viewing angle information, this geometric information is actually used to get this shape representation, and finally how to use this shape representation to do classification. So these are the 3 main problems, and for that, like for initially to get this viewing angle, we make an assumption and I'll go through it. So given an input frames, what we do is like we do k-means clustering to find 8 distinct frame. So what after getting this 8 distinct frame, we assume like these 8 frames are taken from 8 corners of a cube, because that's the most distinct view that you can get. So like to explain in more detail, like if 2 different tactile frame has high overlap between them, like they will be usually clustered within the same cluster. So when we do this k-means clustering, finally we will get 8 distinct views which has very less overlap. So if it has very less overlap, that means like the most common geometric structure that we can assume is corners of a cube. So if you have an object, to get 8 distinct views, like you usually position the camera at the corners of the cube and then render the image. So we assume the same thing here. After doing this k-means clustering, we assume that 8 tactile images correspond to are taken from these 8 different views. So this is not always right, but still we find that doing this assumption gives us a really good result finally. So this is how the whole training pipeline looks like. So first we'll have the tactile image, we pass it through a backbone which is a ResNet 18 model, and we get this image features, and then we construct a view graph. So here we do this clustering and choose 8 distinct feature and then assign them to each corner of a cube. So now the view graph is constructed. After that we use an existing view model called ViewGCN, which is popular in 3D shape classification from multi-view images literature, and we will go through the model details in the upcoming slides. So but this is how the whole training pipeline looks like. We at each iteration, like, we take this features from this VGCN and concatenate it at different levels and finally use that for shape classification. So this VGCN consists of 3 main modules, like local graph convolution, non-local message parsing, and then sampling view selector. So this local graph convolution does graph convolution for this each node features and then update it based on its neighboring features, and this non-local message parsing updates each features based on its relationship with every other feature in the graph. So like even if our initial assumption of viewing angle is wrong, like this will update it the features properly so that we will have better accuracy. And finally we do this sampling view selector, which coarsen the graph so that this representation will be more condensed and then finally used for this classification. This is similar to downsampling that we do in all models like ResNet and UNet. So we'll go through each modules now. So in this local graph convolution, it's similar to this normal convolution we do in image space. So when we have a center pixel and we'll apply a kernel which will do this averaging based on the kernel weights around its surrounding pixels. So in graph convolution also we do the similar thing. We choose a node feature and to update it we find its neighboring nodes that are connected in the graph based on this edge values, and these edge values are calculated from this adjacent matrix, and based on that we will update each of these node features. So this is how the update formula looks like. So this psi is MLP layer that is used to introduce nonlinearity, and this adjacent matrix is calculated from this viewing angle that we initially assumed, and this FL is the node features, and to construct this feature matrix we assign each row as these node features, and this W is a transformation matrix that we apply. So the next module is non-local message parsing. So here this helps in learning long-range relationship among the features. So earlier we only updated the feature based on its local neighborhood. Here we update it based on all the node features. So here we use MLP layer to find the relationship vector between every other node features, and then we update each node feature based on its relationship with every other node features using this formula. So this helps us like cover up our assumption of like assigning this view, like even if it's not an adjacent view, like this will update it properly so that we'll get final results, like a better results. And finally we do this selective view sampling. So this helps in coarsening the view graph and get a feature that can be used for classification. So normally what people do is use furthest point sampling and use that and ignore other views, but rather than that, like what we do is like select a sample of furthest point sampling. Like we first get the furthest point sampling and take its neighborhood views, and then we predict the class label using all the node features, and we will keep what keep a track of like what are the informative node features that can be used for object classification and use those and ignore other views. Like here you can see, like we take furthest point sampling and then we get this neighborhood features and see which are most useful for classification and only use those neighborhood features. And in this way, like, we coarsen the graph, and finally, like, we will use these features. So yeah, the total loss function looks like this. This L shape takes features from this ViewGCN at every layer, and then concatenate it and predict the shape based on that. And this summation view loss is calculated for this shape coarsening. So in that, like, we pass the sampled node features and use those every features to predict this object shape. So we are doing summation across every node features and across every layers, and this makes sure that every node features that we sample is highly representative and can be used for object classification, which is our downstream application. So now we come to this experiment session and baseline comparison. So these are the baselines that we compare against, and this first model is a model where they use just CNN and concatenating the features to do classification. And the next method, they consider it as a sequential problem and use this convolutional models. So here we can see, by adding this geometric information of view angle, we get a much better accuracy compared to our baseline models. So this geometric information really helpful in this object classification task. And we also do a ablation study of different viewpoint configuration. So rather than having a cubic structure, if we do k-means clustering of 12 and sample points along a circle, like equally spaced 12 views, we see whether increasing the number of views, whether it's helpful, and we notice that it's not that helpful, since if you are sampling 12 views around the circular region, like, there will be a lot of overlap, and using a 8 itself is giving really good results. So, and this is the confusion matrix of our model while on the test data set, and here you can see, like, it's mostly predicting everything properly. There are only like few classes it's misclassifying, and most of the classes, if you see, like spray can, board eraser, chain, battery, and like scissor, like, these are lightweight objects where most of the other baseline also have issues with, since when the object is light, tactile data will be very low and it won't be that much informative of the shape. So in conclusion, like, we want to conclude, like, adding this geometric information to this tactile information really enhances the feature representation and can lead to improved performance in downstream application. And in our case, like, we show it really helps in object shape classification. And one of the future works that can be extended is, like, instead of relying on the assumption of tactile view by doing this k-means clustering, if we can get the actual ground truth angle information from sensors like IMU, this can significantly increase the accuracy and the results also. So thank you everyone for your attention, and now we can move to this question answering session. Thank you.